So today, I'd like to introduce something called Euler's method, named after the famous mathematician Leonard Euler. Well, this is very similar to something that we had done earlier in the year. It's called a tangent line approximation or linear approximation. And it's something where, if we know a point that's on a function, but maybe we don't know the equation itself, we can estimate what different values of the function might be. But what's required of us is we must have the slope. We must know the derivative at that point or somehow have information about the slope there. And the theory goes something like this. If you know the equation for a tangent line, you could approximate certain numbers that are really close to that known value, to that initial value. So if you were trying to find 2.02, that'd be great. Or 1.91. Those are both very close. One's a little bigger than 2, an x-coordinate of 2. One's a little smaller. But that tangent line is very, very close to the actual function there. However, when you start getting to numbers farther away, now the error between that tangent line and the actual function gets larger and larger. In fact, we hit a certain point where it probably doesn't make sense to estimate things using a single tangent line. It's just not accurate enough. However, as a quick review, this is what we would do. Find your slope at that specific point, plug in 2 and 1 for x and y. And even though it's hard to see there, the slope would be 5. Then write the formula for that tangent line equation here. Once you have this equation, you can plug in any x value that you want. And it will tell you the approximate y value there. But once again, only if it's very close. Now, I'd like to do one more bit of review before I talk about this new Euler's method, and then we'll see what can happen. So here's the review bit. When you're looking at how a function changes, this blue graph of the function, delta x represents how much the x values change, and delta y represents how much the function or the y values change. So at a point like 3.2, you can see that delta x is 1.2, and delta y, you'd have to calculate. You'd need to know the exact function. When you're looking at these changes on the tangent line itself, we call these values dx and dy. Dx and dy represent how much the tangent line itself changes. So when we say a derivative is the slope of the tangent line, I'm really saying the change in the y values on the tangent or the change in the x, the slope of the tangent, is your derivative. And I know that that's the same slope as the curve at that one point, but it won't be for everything else. Tangent lines are great approximations if you're close by, but if you're not, if the tangent line is not your best option for estimating because x has changed by too much, we use Euler's method. By the way, take a look at that funny spelling. That is pronounced Euler's. I know it looks like Euler's, but that's okay. And these notes on how to do it are actually listed in your book, but I want to show you how to use Euler's method in an example in the next video. But right now, I want to talk to you about what Euler's method is. Euler's method is using a tangent line approximation again and again and again. It's the same thing as a tangent line approximation. It's just we might have to do it multiple times. If you get too far from this first tangent line, the error becomes, shall we say, significant. But if you stop partway along and then check the slope again at this new point and create a new line that's tangent to the graph, or at least has the same slope as the graph, we'll start from this ending point. We're going to use the same slope that we have up there at the tangent line. And then we go a little ways further and we use another one. Well, we get a much better approximation. This example, not so good. Why? Look how big the distance is between different x values. Look how far we go on each tangent line. You can see here where these series of tangent lines can follow the graph fairly well. But notice what happens here. If you have small steps between each function, like 1/10, you can see where the blue function comes really close to green. Green's the original. But as you make your steps smaller and smaller, you make a new tangent line every hundredth. That red graph is almost a perfect replica of the actual function.